So here's how we can use prime factorizations to simplify fractions elegantly. If you recall, the multiply across theorem says that if you have two fractions here, the way we multiply is we just glue them across the top and across the bottom. But if you read it from right to left, it says that if they were already glued, you can unglue them and unmultiply them across. This is the key, along with the prime pieces, to factoring or simplifying fractions. Look at this example. So the 12 is made up of a 2 and a 2 and a 3. Those are its prime pieces. The 20, on the other hand, is made up of a 2 and a 2. That's 4 times 5. 2 and a 2 and a 5. This is by times table. I've broken it up into the prime pieces. Now I could say I could focus my attention on this times and that times, and I could say, you know what, I could unglue those. This would be 2 times 2. Whoa. All over 2 times 2 times 3 times 5. And that would be by multiply across theorem. Meaning that if I was to multiply across, that would get me to the previous step. And now, whatever is common, the common prime pieces, see the one on the top I had 2 and a, here's what I had on the bottom, a 2 and a 2 and a 5. And on the top I had a 2, a 2, and a 3. And basically we say, you know what, let's just unglue them here, separate them, and kill the things that are common. And now we're left with a 3 over 5. And so this becomes 1 by the just 1 theorem. 1 times 3 over 5. And of course that becomes 3 over 5. By the multiplicative identity, the 1 does nothing. And this, my friends, this is how you simplify fractions elegantly. So perfect, step by step. Flawless reasoning, so beautiful. And the key here is math. Whenever you see the times here, you can unglue them like that and then cancel whatever's common. You could have also done, for example, you could have said, oh, this is 2 times 6 and this is 2 times 10. Oh, that means that it's just 2 over 2 times 6 over 10 by math, and then you could cancel that. But the trouble is with that, the 6 and the 10 are still, they still have things in common. You can simplify some more. What you're doing by prime factorizing is you're exposing all the guts, you're exposing all the building blocks, and you can see exactly what's common. You can see that not only a 2 is common, but another 2 is also common. 2 2's are common. And whereas here you may not see it if you don't finish the prime factorization. You may not see it right away. That's the power in prime factorizing. You get to see exactly what's common on the numbers. This number right here is super famous. This number right here is often called the GCD, the greatest common divisor. So we could say that, sometimes people say like this, the greatest common divisor between 12 and 20 is equal to 2 times 2, or they can say it's equal to 4. Greatest common divisor between 12 and 20 is 4. That's another important use of prime factorization. It lets you see the greatest common divisor in the most elegant possible way, by just looking at what are the common prime pieces. Okay, let's do that. That was so fun. Let's do it again. How about we do 150 over 275? We're going to do a couple things. We're going to simplify it. We're going to see what the greatest common divisor is, and we're going to simplify elegantly. Life is too short to simplify unelegantly. Here's how you could simplify. The top I know is a 5 times, actually it's a, I could say that it's a 10 times a 15. On the bottom I could say that's maybe a 5 times a 55. So that's by times table. And I'm going to be careful to finish the prime factorization so that I can really see what's common. So this is 2 times a 5 times a 3 times a 5. On the bottom I have a 5 times a 5 times an 11. I reckon that's all the prime pieces we have. We cannot factor it anymore. Those are prime factorized. And I can see exactly what's common. I see a 5 that's common. Both of them. I see another 5 that's common. And I see that's about it. So I have 5 times 5. I'm going to set them aside for a second. Times 2 times 3. All over 5 times 5. Times 11, and of course these are all times, so I can have a commutative law of multiplication and associative law of multiplication just to rearrange the things. There's no plus here. I don't have to worry about breaking up terms. It's all just one term on the top and one term on the bottom. This, of course, I can see the end of it. I'm going to unglue it and kill this, and that's going to be the answer. And not only that, but I can see what the GCD is. The GCD, I have trouble spelling GCD. 150, 275. What's the GCD? It's 5 times 5, which is 25. This is as a little side bonus. You get a very, very elegant way to find GCDs. You just put them as fractions and look at the common prime pieces. Alright, let's continue here. So this becomes 5 times 5 over 5 times 5 times 2 times 3 over 11. And that's by multiply cross theorem. This is what allows you to separate. The thing came off. Alright, this is what allows you to separate. This becomes just 2 times 3 over 11. This is by JOT and MID. That stuff is gone. Yippee-ki-yay. This is called simplifying a fraction elegantly. It's so powerful. It not only works for regular numbers, but it works for every fraction that you will ever do in your entire life. And no matter if it's polynomials or functions or crazy stuff like this. Here, let's try this one. This one I'll break up into prime pieces. This is 2 times 5 times x times x times x times x. Right? That's what that 4 means. Write it 4 times. On the bottom I have 5 times 5 times x times x times x 3 times. This is by natural exponents and of course times table. And now I can see exactly what's common. I have an x that's common. I have another x that's common. I have another x that's common. I have a 5 that's common. And I believe that's the greatest common things that I have. There's nothing else that's common. So I'm going to separate it like this. I'm going to go like this. 2x times 5x to the third. And on the bottom I have a 5 times 5x to the third. Okay, I've separated it so that I can see the greatest common divisor here. Now I unglue it together, so that becomes 2x over 5 times 5x to the third over 5x to the third. That's by math. And of course this gets killed because it's equal to 1, so that becomes 2x over 5 times 1. That's multiplicative as identity, and prior to that it was JOT to kill that. And there we go. I've simplified the fraction elegantly. So beautiful. And as a side bonus, I can also tell you what the GCD is between these ones. The GCD between 10 and x to the fourth, sorry, 25 x to the third is equal to the greatest common things that I canceled. The greatest common things that were prime blocks that I could see was a 5 and 3 x's. That's the GCD. If you ever need to find the GCD between two items, put them as a fraction and see what can you cancel. And that would be one way to understand the GCD and to easily wrap your head around it. Okay? Powerful stuff. Let's see.